This video is going to focus on exponential equations, building directly off of what we learned in our previous video in which we discussed relative rates of change. So let's take a look back at that previous video and then connect it to where we're going in this one. So if you remember in the previous video, we looked at two situations in which we were given an annual growth rate or a growth decay. And we created from that what we would refer to as a growth factor. We said, well, every year, if the price of milk is increasing 3.7%, then the next year's price would be 100 plus that 3.7 times more than the previous year. And from there, we build that growth factor. And we realized if we're multiplying by that growth factor multiple times, then we could sort of shorten that with just the growth factor to the number of years that have gone by. And that sort of growth factor exponent then got multiplied by sort of the initial price that we started from. Similarly, when it was decaying, instead of adding the percent to the 100, we subtracted it. And from this idea of the 100% plus or minus a annual rate times an initial value, we build our exponential functions. And so you'll see here in this equation, right here in the parentheses, we have that 1 plus or minus the relative rate of change. And right there, that's our growth factor. That's how much, we're multiplying by. It's getting bigger every year. And then this piece right here, that's our annual growth rate. And it's not necessarily annual. I'm going to put annual in parentheses. It's sort of a single unit in time growth rate, typically annual, but we'll look at somewhere it's monthly or hourly or so forth. And it's written, even though the problems will give it as a percent, we write it here as a decimal. And so we need to be comfortable taking our percents into decimals. The input letter then is the sort of power, the number of years, the number of hours, the amount of times, the number of times we're multiplying by that growth factor. And then we have our sort of initial value, and then we get the output. Down below, you're just going to probably see a form that you might be a little more familiar with. You might have seen in a previous math class. To sort of give you a sense. Obviously, just like with linear functions, we want to use meaningful letters when we write our exponential equations. So we're going to take this equation and we're going to sort of use it in two different situations and sort of create a more sort of formalized way of doing what we sort of reasoned through on the previous problems. Maybe the years aren't quite as easy to multiply out like 2, and so having that function capability makes life a little better. We're also going to be bringing in that graphing calculator again with some of these problems coming up, so make sure you got your Desmos app handy. Okay, so we're going to start with an exponential growth problem. I'm going to change colors just so we don't mix up our green with another one. So we're looking at population, and with exponential functions, population's a common one because it's often our population doesn't grow sort of at a constant rate. We often talk about populations growing based on a certain percentage. So the U.S. population was 282.2 million in the year 2000, and we could say from the year 2000 to the year 2017, the population was increasing around 0.8% each year. Notice that's less than 1%. So we want to write an exponential equation that models this population growth. A good thing to keep in mind is what year you're starting with. When it comes to years, you don't actually put the year in itself. You usually track years from a certain point in time. So I'm going to use T for years, and we're going to make that year 2000 our year 0. So we're going to say T is years since 2000. I love tracking years from those nice even numbers because it's easy to count from 2000. Makes the math a little simpler. And then whenever I deal with population, I tend to go with P because population starts with P. So the population of U.S., and it's in millions of people because we're not actually going to list out all those zeros, so I need to make a note that it's in millions. All right, so if we're setting up, our output letter is P, And then we're going to have our initial value. Well, the initial value here would be the population in the year 2000, because that's our year zero. And that was the 282.2 million. So I'm going to have 282.2 million. And then we're going to times that by 1 plus the relative rate of change, so that annual growth rate. Well, in this case, that was 0.08%. I'm going to write that up here. Oops. It helps if I put my decimal in the right spot. So 0.8%. Now that's not in its decimal form. Don't be fooled. That's still in its percent form. If we want to put it in its decimal form, we would divide by 100, which basically means that would move the decimal point 2 places to the right. So that would be 0.008. And so that's actually going to be our R value. That's our growth rate as a decimal. And then that whole growth factor, we're going to raise it to the T power, T representing years since 2000. And so we could leave it in this form. There's nothing wrong with that. Though often we're going to see that sort of growth factor combined into a single number of 1.008. And I would then end up with this being my exponential function. You might ask, well, what should I round my growth factors to? It really depends on the situation. In this case, I didn't want to round it at all. I want to keep as many decimal places as possible. All right, moving on to the next. We now have this model. Well, we can use the model to make predictions. So it's saying, based on this model, what would we expect the U.S. population to be in the year 2023? Now, 2023 means we're looking for 23 years past 2000. So using a method like we used up on number 2 from the previous video is probably not going to be very realistic. I'm not going to want to multiply out 23 times. This is where the model becomes really nice to have. So I'm going to say, I want to find my population 23 years past the year 2000. And all I need to do is plug 23 in for T. And I'm going to put this whole thing in my calculator. And when I do, I get out 338.96 million people. And ta-da! I wrote an equation to represent my situation and then used my equation to help me answer a question. All right, in this next problem, we're going to be looking at an exponential decay situation. In this particular problem, it doesn't outright say decreasing or decay, but you're told that oxycodone is metabolized. And so for those of you who don't know what that word means, it basically means it's being broken down by our body at a rate of 18% per hour. So this is one where we won't have necessarily an annual growth rate, but it will actually be an hourly growth rate. So we want to write an exponential equation that models the metabolizing of oxycodone if a person is taking 10 milligrams of the pill. So let's start with our percentage. So we're basically have a negative 18% is our rate. And so just like when we talked about on the previous problem, we're not increasing by 18%, we're taking it away. And so when we think about that, what we actually have is the 1 minus 0.18, which would tell me that my decay factor would actually be 0.82. So that's what I'd be multiplying by every hour to figure out how much is left. So after 1 hour, there's only 82% of the amount from the hour before that still remains. So we started with 10 milligrams. Again, we need some meaningful variables. So I'm going to use M, and that's going to be milligrams of oxycodone. And I used M instead of O because I don't really like using O as a variable. Looks too much like 0. Our initial value is 10, And then we already did that 1 minus 0.18, but I'm going to just write it out just so you can sort of see it. And then I'm going to use H instead of T, and that's hours since taking the medicine. Just, you know, as whenever you use variables that aren't, it's good in a context, it's good to say what each represents. And again, just like with the last one, we could simplify this down a little just to make it a little easier. And that's where the 0.82 will come into play, and it's still to the h power, and ta-da, there's my exponential function. Now I'm going to use this to answer two different questions. So the first question is just, okay, now let's just do some calculating with this. We want to figure out how much medicine's left after 4 hours and then after 12 hours. And so in both of these cases, we're going to be replacing h with these numbers. So if I'm looking at the 4 hours, the amount of medicine would be equal to 10 times 0.82 to the 4th power, and that would come out at 4.52 milligrams. Same idea with 12 hours, and notice I should be getting less and less medicine. If I set up my function correctly, the medicine should be dissolving in my system. And so 10, 0.82 to the 12th, and I get 0.92 milligrams. Okay, so that's when we are given the input and we want to find the output. What if we have the reverse? What if I want to estimate when there'll only be 2.5 milligrams left in a person's system? You might be going, well, why would I want to do that? Maybe it's like, I can't take a second pill till I know, I only have a certain amount left, because otherwise it would be too much medicine in my system. And these are questions that doctors and pharmaceutical reps have to think about. And so the reality is, in this case, we're actually solving an equation. We're saying, okay, if M is equal to 2.5, what would H need to be? And so there's some options here, and I'm going to give you two. One, you can guess and check. And I am totally okay with you doing that. You can plug in some values for H, and you want to get as close as possible to 2.5. The other option is to graph. And so I'm going to show you both methods and then let you sort of pick which one you like better. So this is where I said you wanted to have your Desmos graphing app handy. So I'm going to flip over to mine. So here's my Desmos graphing app. I'm going to take out that equation. I'm going to type in. And again, with Desmos, we need to use y and x. So 10 times 0.82, and then we're going to raise it to the x power. And so notice my graph is very small, so I'm going to zoom in a little. Okay, so I got a nice pretty graph here. Actually make it a different color so you can see it a little better. Here's my function. So option one is to simply go, okay, I have an exponent there. I need to sort of figure out what it's going to be. If I think back to the problems I just did, after 4 hours, I had 4.5 milligrams. After 12 hours, I had less than 1 milligram. So I'm looking for a number bigger than 4 and smaller than 12. And so I could start plugging in numbers. So I could say, okay, 5. Okay, 5 put me at 3.7, not quite there. Okay, 6. 6 put me at 3, not quite there. 7. Ooh, 7 was a little too much. It was close, but not quite there. So I could try and get more specific, and I could go, okay, 6.5. Oh, that's too much. 6.8. Ooh. Okay, look, I'm getting a little closer. 6.9. Oops, 6.99 was too much. And so you can sort of play with numbers till you sort of get one that gets you pretty close. You sort of play till you sort of see. And so I could say, okay, 6.95 is pretty close. So that's option one, and that's perfectly acceptable for this class. We're getting estimates here, and that's a very good estimate. So that's one way. And so you just sort of have to be comfortable with sort of playing with numbers and sort of getting to where you need it to be. The other option is similar to one we looked at earlier with linear functions, is I would graph this original function and then I'd graph what I want that output to be equal to. So in this case, I want it to be equal to 2.5. And you'll notice, okay, so I have a line here and I have my exponential function and I look at where they cross. And so in this case, they cross at 6.986. And so if I go back to my problem then, well, 6.986 hours. And that was about what we got with guessing and checking. If you remember with guessing and checking, we had 6.9. So we were pretty close with guessing and checking. I find the graphical method a little quicker, but it's really what is your comfort with? And the key here is understanding that the 2.5 is the output. That's what I really want you to get at from this. So hopefully from these problems, you have a sort of general sense of how we might write an exponential function and use it to answer some basic questions. In the next videos, we're going to look at some special cases with them.